Two of the most important properties of graphs are whether or not they contain cycles and whether or not they are connected. We begin with a discussion of cycles, which are also referred to as circuits. What constitutes a cycle differs depending upon whether the graph is directed or undirected. There is one aspect that is common to both types of graphs, so let's begin with it. The determination of whether a graph contains cycles is best done by performing a depth-first graph search. Because a graph can be disconnected, it is important that the search start from every vertex that has not yet been visited, because it is possible that there may be a cycle in only one of the connected components. Next, let's consider the difference between a cycle in the two types of graphs, beginning with undirected graphs. Because the edges are undirected, a cycle in an undirected graph must have at least 3 edges. Cycle detection occurs when a vertex in the graph is reached that has already been visited. So to prevent cycles of length 2, we must avoid returning to the previous vertex when performing the depth-first search. There are several differences when the graph is directed. First, unlike an undirected graph that requires a minimum of 3 edges, a cycle in a directed graph can consist of a single edge going from and to the same vertex. Next, all the edges of a cycle must go in the same direction. Finally, to determine that a cycle exists, it is necessary to distinguish between reaching a vertex that has been visited with one that has already been visited along the same path. Using 2 separate marks is one approach. Another is to use 3 states: undiscovered, meaning never visited; discovered, meaning encountered along the same path; and finished, indicating it is being visited for the last time. Connectedness is another important property. The fundamental definition is the same for both directed and undirected graphs, which is that a graph is connected if there is a path between every pair of vertices. But in the case of a directed graph, there are 2 ways to interpret this definition. But first, let's begin with the undirected case. To determine whether an undirected graph is connected, we can perform any type of search, starting at any vertex, and upon completion check whether each vertex is marked. If they are all marked, the graph is connected. With a directed graph, there's 2 types of connectedness. A graph is strongly connected if it is connected in a directed sense, meaning there is a directed path connecting every pair of vertices. Weakly connected means that it is connected in an undirected sense, ignoring the direction of the edges. Clearly, every strongly connected graph is weakly connected, but the reverse is not necessarily true. Let's look at a visualization of cycles and connectedness in undirected graphs. So we'll start with this example and ask the question, is it connected? And the answer is yes, that picking one vertex here, every other vertex is connected to it. Does it have cycles? And yes, indeed, it has 1 cycle. The question of whether it's a tree, sometimes referred to as an undirected tree, will only be true if it's connected and has no cycles. So in this case, we should expect it to be false. All right, let's make one more, and perhaps this is an example of the opposite. So in this case, if we ask whether it's connected, the answer, of course, is going to be no, because both of these 2 vertices cannot be reached from that one. Does it have cycles? In this case, it's not, well, actually, it's going to have 1 cycle right up here in this corner. So if we ask that question, yes, it has cycles. And so for both reasons, it's not going to be a tree. Now, regardless of whether a graph is connected or not, every graph consists of a set of connected components. There are several ways to determine the connected components of a graph. One approach uses a data structure called a disjoint union. A depth-first search that includes a sweep starting at every unvisited vertex can also be used. Since there's two kinds of connectedness with directed graphs, there are also two kinds of connected components. Strongly connected components are ones in which every component is strongly connected. The algorithms for finding strongly connected components are somewhat more complicated. Weakly connected components are one in which every component is weakly connected. With every directed graph, there's a corresponding component or condensation graph. The condensation graph reduces each strongly connected component to a single vertex. Let's consider two directed graphs and examine their weakly and strongly connected components and their corresponding condensation graphs. The top graph has two strongly connected components. The first consists of vertices A, B, and H. The second consists of the vertices C, G, and J. It is weakly connected, so it only has one weakly connected component. The condensation graph reduces the two connected components to two vertices. A, B, and H are reduced to A, and C, G, and J are reduced to C. There's an edge from C to A in the condensation graph because there's an edge from C to B in the original. The bottom graph also has two strongly connected components. D, F, and K are in one, E and I are in the other. Like the one above, it is weakly connected, so it only has one weakly connected component. The condensation graph reduces the two connected components to two vertices. There's an edge from E to D in the condensation graph because there is an edge from E to D and an edge from I to D in the original. Either edge would be sufficient.